the starting point is to assume that you have a table of data with unknown structure. So it could be data you have generated or you got from somewhere else, and it's maybe a TSV file or a CSV file, and you have some just text data and we don't know what it is. So maybe some of it is gene IDs and some is maybe proteins and some is we don't really know. And now the challenge is to make sense of this data automatically as far as we can, to provide a context and maybe also to prepare it for publication. And this data is only an illustration. That is not a real data set. It's a generated data set that I made up for this demo, but I believe it reflects a real situation. So where do we go from this? So in Edelweiss, we provide tools that allow you to automatically upload the data and then to generate data servers, API servers, and data browsers from this. We call it the Data Explorer. So the first step is you upload that file that I just showed you in the previous slide. We just upload it as a TSV file, and then we get the schema editor. And the schema editor has been able to guess maybe automatically the data type of many of your things. We can see here that some are IRI or URL, and some are strings, some are integers. And we can choose if they're going to be searchable, and we can give them a description and give them a short name. And we have already a best guess available. The system made a guess for us. But if you want to improve, you can make adjustments here until you're happy. That's the first step. And then once you've made your adjustments, you click Publish, and then you get the Data Explorer. And the Data Explorer can be filtered. It's going to look like this. What you see here is a ToxRefDB Data Explorer. So it's not for the data I just uploaded, but when you've just uploaded that data, it will look like this. So you will see the various fields, and you can search it, and you can filter it, and so on and so on. So the idea then with the Edelweiss system, bringing in all this, is you start from unknown data. We know nothing about the structure, but then we do this Edelweiss schema discovery, where we try to discover the structure by using an Edelweiss knowledge base, which can make a best guess or a best effort guess about what's in this data, what is the meaning of every column. And then we perform Edelweiss data integration, where we combine the data with other data sets, possibly insofar as you want to and insofar as it makes sense. And we do that by making use of linked open data from known ontologies. So these can be public data sets already on the web, on the internet. And all this is then stored in Edelweiss storage in the pre-integrated form as well as in the post-integrated form. And these data sets can then be made available on the APIs or on Data Explorer. And APIs can then provide the data on Jupyter notebooks, on Python or on R, or in other APIs. So it takes care of the whole workflow from integration, ingestion of data, unknown data, to integration, to storage, and then to publication in various forms. And publication can be internally inside your lab, or it can be publicly on the web to external users. And the Edelweiss concept, what the knowledge base is trying to do is, by storing information in this domain about common identifiers, such as genes, proteins, small molecules, pathways, and the patterns of such identifiers in this life science domain, we can mostly guess the content of many text files. And then we map such identifiers, once we have discovered them, to ontology terms, i.e. IRIs. And then we can turn text files to linked data automatically. And we can integrate such a file with suitable external data sets automatically, thus providing a context and thus generating this integrated data set automatically. And then just, looking at that again as a flow chart, you take the unknown data, you perform the schema discovery, and then the Edelweiss knowledge base has integration patterns, and this knowledge base is a resource that we keep extending over time. So we keep adding information to it about identifiers from proteins or small molecules or pathways, ontology terms, and so on and so on. And then we store all this in the Edelweiss storage. So for example, in the example I just showed, in that unknown data file, we identified successfully ensemble genes and proteins and geoterms, and we have degrees of confidence. So some of them we're very confident, and some of them we for example, if it's just an integer, maybe we think it's a geoterm, but we're maybe not sure, but we make a best guess. And if it's just a number 31, then we can't really guess. So in some cases still human intervention is necessary. And this of course, is the concept. You should guess as far as possible, but we shouldn't guess what cannot be guessed. So if we see a column that contains only uniprot proteins, and then we're quite confident about that, then we make a guess from the knowledge base. I think this column is only uniprot proteins. If we see a column that contains mixed identifiers, where we recognize a few things, but we don't see a pattern, then we can't classify it, because then we're not sure. So the confidence has to be quite high for every column for us to make a classification. So again, going back to this table from before with unknown structure, what does it look like concretely when we perform the discovery and integration? The post-discovery here, we have green columns and yellow columns and red columns. And green columns are, we are very confident we were able to successfully guess exactly what it is. And then yellow columns are, we think we know about the geoterms, for example, but we're not 100% confident, so please confirm. And red columns are, we don't really know, so users have to tell us what it is. We can't automatically infer. So realistically, this will always be the case. So some of the things maybe you have introduced as new data types. So, but still we can perform a good guess, and we can integrate many columns, and this is where your external data will come from. So when we have performed this guess, when we have, for example, a uniprot column that we're very confident about, then that can be a basis for column discovery. It can be a basis for integration and data fusion, and then we can generate a fused data set. So because the knowledge base also contains information about what are some additional data sets that I can combine with uniprot columns. So in this case, for example, concretely, it can look like this. So we can find this blue column here, the gene name. We can discover gene name based on uniprots, and then suddenly you have more information in your data that you did not have before. And that's just one example. There is maybe 10 or 20 or even hundreds potentially of different columns you can potentially discover from uniprots just based on identifying correctly what is uniprots. So bringing all that together, you give your raw file to Edelweiss. We discover ontologies, IRIs, and linked data columns as far as possible automatically by the knowledge base. And then after we have that, we can discover additional columns from other data sources. And then everyday users can see, yes, we don't aim to confuse your users. So if you don't want to see these IRIs, or you don't want to see these RDF terms, then we can hide that from you. And then we can show the data set as it was originally inserted. So there will be no confusion. So, but then optionally, people can choose to see this IRI RDF layer if they want to. And then you can generate this linked data version or an integrated version of your data set and publish all of that with a click. And then we provide a data explorer, we provide API access and versioning and provisioning features also under development to help you control access and to help you manage different versions.